Okay, well, anyway, I just wanted to thank the organizers for putting this workshop together. It was really exciting to learn about the rover and also some of the potential payloads that, are considerations because there's really exciting options. And so I'm actually excited to talk to you about one of those. So it's an instrument that we have been developing with funding from NASA's DALI program to mature the Advanced Multispectral Infrared Microimager, or AMIM for short, which is kind of similar to the previous presentation, which is a multispectral microscopic imager that is able to image rocks and soils up close at the microscale, but it's kind of combining the capabilities of an imaging remote sensing instrument, but applying it at the microscale. I just want to thank my colleagues who contributed to this, and this is actually an image that was taken with our instrument of basaltic regolith sample from the Kawi Desert. Next slide, please. Yeah, so as the previous presentation noted, right, microscopic imaging is really powerful technique and it really enhances planetary surface exploration. And of course, lessons learned from exploration with rovers, right, from Mars mission, really is, being able to, the next step is being able to have compact instruments that can really enhance science return by, supporting real-time hypothesis-driven exploration. It's key and something that a pressurized rover could be able to do with these type of capabilities. This is sort of like the concept art here on the left. And as the images below, right, microscopic imagers have flown on past missions like the Mars Exploration Rovers, MSL, Mars 2020, and really provide valuable information about surface textures as well as regolith properties. And just like the example below, right, on the left, right, which is the famous blueberries, right, that were detected by MER. And then similar on the right, also those, reduction spots called leopard spots that have were recently discovered by the Perseverance rover in Jezero crater, which suggests, really evidence of aqueous activity. And so the next step, right, is really combining sort of mineralogy with microtexture is really a powerful tool for planetary science. Next slide. It would be enhance the capabilities of a rover. And so AMIM, as I mentioned, right, really combines microscopic imaging with microspectroscopy, and is really enabling to not only understanding and mapping minerals, right, and ices in situ, but for understanding the geology of planetary surfaces, right? And so in this case, for example, for the moon, like understanding origin, evolution of the lunar crust, as well as properties and composition of the regolith, but also being able to map, right, at the microscale, sort of the composition and distribution of volatiles. So for example, like water ice or even other volatiles that may be present in, for example, in PSRs. And then of course, right, with AMIM, because it's an imaging spectrometer that goes from the visible all the way out to the midwave infrared, right, so 3.6 microns, we really can help provide ground truth data for orbital measurements. And so as being able to do spectroscopy, we can detect a wide variety of minerals. So like in the upper right, it's an image just kind of showing that AMIM potentially deployed on a robotic arm and the type of capabilities that it could provide. But because it's also uses active illumination using LEDs, we bring our own illumination. And so we don't have to worry about shadows or being actually in thermally shadows or, effects from lighting that can really sort of, can be a very challenging environment, especially for remote sensing instruments. And so the instrument is composed of sort of three main elements for illumination system, right, of sort of these multispectral LED arrays. An adjustable focus mechanism that allows us to not only image near and far, so we don't have to be super close to the sample, and we can image samples that are unprepared surfaces, but also we can also do like Z-stacking to be able to get sort of topography, microtopography. And the instrument also includes visible and midwave infrared detector. Next slide, please. And so this is just kind of a concept art of what the instrument could be, right? Developing. And so again, AMIM sort of really combines that spatially correlated information about mineralogy and microtexture, which is really important to be able to kind of do petrology in situ. And so AMIM does, can do fine scale imaging, right, which is important for understanding sort of regolith properties, right, grain scale textures, but also within a really decent size that you can sort of connect the microscopic imaging with the remote sensing images. And of course, by enhancing this with fine skin mineralogy, we can detect a wide variety of minerals. And of course, because we have active illumination, we can operate both in shadows, daytime, and we can also operate a variety of distances. Next slide. And, and so then this next slide just shows just kind of sort of the idea, right? It uses LED arrays. We have a focus mechanism, and then of course the camera core. And so we have about 38 bands that go all the way from the visible to 3.6 microns, acquiring sort of high definition images, right, with a 1K by 1K array. And we can really resolve grains, fine sand particles basically with 30 microns per pixel. And we acquire both multispectral images with LEDs, right, with a much, about 38 bands up close, but we can also look at longer distances, a smaller subset with a small filter wheel. Next slide. And this is just to give you a sense of the type of bands. And so the nice thing about the LEDs is can you really customize and target specific mineral absorptions to really be able to distinguish between very sort of subtle differences in the mineralogy, but also, for example, we have quite a bit of bands around the 1-3 micron feature to be able to distinguish sort of the different sort of flavors of water. Next slide. And so as you can see, right, but we can see on the left, right, we can distinguish wide variety of sort of mafic and oxide minerals. So we're dealing with, for example, like distinguishing low calcium and high calcium pyroxene, olivine, plagioclase feldspars, different types of oxides, whether goethite or hematite. Similarly, on the right, different kinds of volatiles, for example, like water ice, CO2 ice. Next slide. We also have bands that allows us to distinguish between a wide variety of hydrated minerals, like you see here on the left, but also different types of salts. Next slide, please. And so, as I mentioned earlier, right, by having a wide variety of bands around that 3 micron feature, we can really start to be able to sort of say information about the type of potential, whether you're distinguishing hydroxyl or water. And so, for example, like here in the black plot, you can see that it's sort of the hydroxyl. We can distinguish between hydroxyl versus you're dealing with molecular absorbed water, sort of coating on the grains, right, with the red spectrum, versus right like dealing with water ice. And of course, not only can we detect that within each pixel, but we can map it out. And of course, with these different bands, we can also distinguish between different types of volatiles, whether you're dealing with CO2 ice, methane ice, but also having bands around the 3.4 micron feature, we can also detect organics. Next slide. And this is an example of showing, especially the plot on the right, where you see that sort of 3.4 micron feature. That's critical for organics. Next slide. Okay, and this is just a kind of an image of the instrument that we've developed, the image, right? So you have of the prototype that we've developed on a stand, kind of shown with the different LEDs turned on, so with the blue, green, and red. But we took out sort of the housing just to show the key elements, right? Our illumination system, our adjustable focus mechanism, and the camera core. Next slide. And this is just the type of sort of some of the results. For example, this is like I mentioned earlier, this is a basaltic regolith sample. And so this on the left is the type of image, for example, you get with like a white sun microscopic imager, right, which you can see quite a bit of diversity. But by really going out into the infrared, it's very powerful to distinguish not only detecting the mineralogy, but in this case, by combining it with that microtexture, we can even see, for example, in some of these regolith grains that have already shown alteration. Next slide. And this sample is one that we looked at as actually a regolith sample from Apollo collected during Apollo 14, sample 14259. And on the left, it's upper left, this kind of gives you the image of sort of the Hans lens, sort of the Hans scale version, right? You see it's very fine powder, very kind of gray scale, but by really the power going at the microscale, you can start seeing, especially in the left image, those different elements with the lighter tone. For example, it might be plagioclase versus the regolith grains. But by going out into the infrared, as is shown on the right, you can see now wide, diversity that is present within this regolith sample. And if you go to the next slide, please. Because each pixel is a spectrum, then we can draw like these little circles, ROIs, around these individual little grains and extract a spectrum from these. And so as you see in the plot on the right, we can really distinguish like individual little grains, for example, ones like low calcium pyroxene, high calcium pyroxene, flaget clays, feldspars, right? You know, even olivine distinguishing. But even those, for example, like agglutinates, right? So this is stuff that you would, the power of this capability is that really getting at the individual grain scales, you can identify not only sort of get a sense of the composition of the regolith, but also identify very minor phases that otherwise, for example, if you had like a standoff instrument, you would not be able to see. And next slide. Okay, and so just to kind of summarize, right? So AMIM brings a lot of capabilities, right? By providing the power of having that spatially correlated mineralogy with microtextures that can be used for rocks and soils at the microscale. It really provides capabilities for not only fine skin imaging that allows you to characterize grain morphologies, right? Textures, fabrics, right? Which especially for like the lunar surface, right? You know, very fine grained features such as like fairy castle structures. But also combining that fine skin mineralogy, we can really sort of map out sort of the composition at the regular, you know, at the grain scale, identify not only major and minor phases of minerals, but also a wide variety of minerals that may be present that we're just not seeing from orbit or even from remote sensing instruments, just because they're just in such minor phases. And of course, by having active illumination, we can do daytime and nighttime operation with, you know, independent of whatever lighting is available to us. And so AMIM really provides these capabilities that are associated with orbital instruments, such as like Uncrewed, or Prism that was on Mars Reconnaissance Orbiter, but you know, in a compact size and mass that could be easily deployed on a robotic arm, right, or rover body, or even inside a glove box to help high-grade samples. And so AMIM really enables non-destructive, right, because we don't need any sample preparation, you know, surface preparation, you know, to characterize planetary surfaces, help prospecting for resources, and then helping as well identify high-priority samples, you know, to sample for analysis, whether onboard instruments or potential return. And I think that's it. And let me know if I think it might be one more. Yeah, that's it. Yeah, I just want to acknowledge, thank you for you know, the funding as well as the collaborators, and just kind of concept of how this instrument could really enable future missions. Thank you very much.